Good morning, everyone. Welcome to the third day of this workshop. So we have Professor Wolf. He will give his second lecture. So yes, Professor Wolf. What?
Okay, thanks. Great. Okay, so thanks everyone for coming back. Looks like some people are there. And so I want to continue and do something. So I forgot last time to mention that what I'm talking about is joint work with a number of people. In fact, it's mostly their work, and they sort of carried me. But this would be Emily Dumas, John Lofton, Andrea Tamborelli, and Huiping Pan. I'm hoping that his work will make an appearance here before I run out of time, but it may not. Okay, the other three certainly will. Okay, so last time, you remember, we talked about we had a quadratic differential on C, and maybe I would write it as zk dz squared, but it really didn't matter. It could have, it could have been some sort of polynomial of degree d dz squared. And from this, we built a harmonic map from C to H2, and it had an image. So the quadratic differential, I was always sort of drawing, if I say z to the k, in terms of some trajectory structure, which I sort of indicate like this, trying to draw the leaves of the horizontal foliation. And by looking at a polygon of this, so I'll pick out some leaves and make a polygon of horizontal and vertical leaves. That had an image over in H2. This was supposed to be H2, which was nearly geodesic, excuse me, which was nearly geodesic on the blue, in terms of images of the horizontal lines, and very, very small on images of the vertical lines. And I had made the remark very hurriedly at the end that as I did an exhaustion of the plane by these sorts of polygons, then this would have it on an image that was an ideal polygon, something like that. So I guess it's been a few hours. So are there any questions about this before I go on?
Do you have any questions?
Okay. So I'm going to do something a little bit dangerous. There's something I didn't do last time. I ran out of time, and it's a bit, and I don't know whether I'll ever really use it, but I promised technique, and this is a good time to talk about some technique. So, so I will. And my punchline for this talk comes at the end. So this is what makes it dangerous. I hope I don't run out of time. But nevertheless, so the question that I will just quickly address with an example, a technique I'll address is, which I'll gather it all under the rubric, why are harmonic maps interesting? Okay, so and so of course they're minimize energy, but so what? You can minimize lots of things. And so an answer that I might give is through the chain rule, the Riemannian chain rule, by which I mean, suppose I have a map from M to N, its name is U, and then I have some function on NR. We can look at the Laplacian. The Laplacian is interesting. That's a rotationally invariant differential operator. It actually generates the ring of rotationally invariant differential operators. So that's an interesting thing. compositions are interesting. Laplacian of F composed with U. And so what is this? It's taking two derivatives of a composition. So one could expect two derivatives on F and one on U, or two derivatives on U and one on F. And so, you can pretty much just with that comment figure out what this is. Two derivatives on F has to be the Hessian. It's the only operator that makes sense. And in one derivative, especially sort of Laplacian as a trace, so I'll take the trace of the push trace, not with respect to a frame, the Hessian is happening on N, but I'll take a frame on M and push it forward by U and take the trace with respect to that funny frame on N. And that'll be the first term. And then the next term, will be something with one derivative on F. That has to be a gradient. And then I'm going to dot it with something. Something has two derivatives and a trace. And the point is that that's the tension. Remember, we said that when we have a map that's harmonic, the tension is going to vanish. So why are harmonic maps interesting? Because the Laplacian, the chain rule for the Laplacian reduces for harmonic maps to just be this trace of the Hessian with respect to a push-forward frame. So how is this useful? So we had the theme last time about how we want to take pictures or geometric information, try to translate it into PDE, go look up something about PDEs, find out what the answer, what the PDE estimates tell us, translate it back into geometric information. So what is it we established here, really? What we said was a little bit less than what I drew over on this side. So what we've actually shown, if you look at the estimates, is that if I look at this polygon, the boundary of this polygon, it goes to this sort of boundary here. But what about the interior? Where does it go? Okay, well, here's the point. So here's like the simplest application of this sort of chain rule is that what I can do is, I'm sorry, I have the restriction. I have two maps that are sort of interesting. I have this map U, which is if I make, I don't know what to call this. If I create this domain here, and maybe I'll just call it, I'll just call it domain. Let's see. So its name is domain. So I have some map U of this domain, and maybe I have another map. So I'll just say, V. And V will be maybe a harmonic map to something that's straightens these arcs. So maybe it would be to some domain we would create whose lengths are about the same. Again, we could have something short, but it's really solving a harmonic maps Dirichlet problem. So that's sort of the point, is that I want to solve a Dirichlet problem with geodesic boundaries. So here the domain has geodesic boundaries and I have some solution V. Here for U, I have whatever the boundary goes to, which are kind of nearly geodesic boundaries by our estimates, because it's nearly a projection and with short little connectors. But this is something, this domain over here isn't quite straight. It's close to this sort of straight one, but it's not straight. So So really we have two maps, right? I have the map, so I have U and V. These are taking D into H2, but of course, it's taking into H2 cross H2. So, Z is going into U of Z, V of Z as a pair. And I can look at the distance between 2 points in H2, and that gives me a real number. So I'm really looking at the distance from U to V. And now if I take the Laplacian of that, I'll get this funny trace of the Hessian of this distance. Let's make it smooth. I'll make it distance squared. But the trace of the Hessian, well, I'm in a non-positively curved space, so the Hessian of distance is going to be positive definite. I take a trace, positive semi-definite. I take a trace, and so this is going to be greater than 0. So that's saying that, so in other words, distance squared here between U and V is subharmonic. And so, in other words, whatever estimate I have on, so I'll just conclude something here. So the distance between U and V uniformly is less than the maximum of the distance squared between U and V on the boundary of this domain. And I know that this is really small, so say less than some small delta, because I had the a priori estimates on this boundary that it was nearly geodesic and it was nearly parameterized by arc length. And here this is geodesic and parameterized by arc length. So whatever this error is between this arc and this straight arc, the worse this error is, which is very small, translates to an estimate on the entire domain. Okay, that's just a comment. But it's a useful technique to try to think of what is the relevant chain rule to apply in the circumstances that you're studying. And I'll just say often you can compute this sort of Hessian. In fact, in this case, you can get a better estimate by computing the Hessian. So maybe not just that it's positive, but maybe that it's in sometimes you can get something like it's bigger than C times distance squared and get exponential decay. Okay, so but I don't quite have that, so I better cross it off. Okay, so now I'm ready to start my next lecture. I wasted a lot of time doing that. I'm very sorry. Okay, so now let's go to what I really want to talk about today. And so last time we talked about harmonic maps from complex plane to H2. And today I want to talk about affine spheres, and this relates to representations SL3R and convex real projective structures. And so why write all this? The idea is you're supposed to think, oh, this is a completely different topic. But in fact, it starts off as a completely different topic. And then whatever analysis we just did on the previous lecture, we mimic in this setting, and we get similar results. But oddly enough, the results we get are more complicated, and through the complications, we actually see things in the previous example that were so oversimplified, we look past them. You'll remember that I highlighted last time this Stokes phenomena. So maybe I'll just say this again. I'll just write Stokes phenomena. And sorry, there's writing's term. And here we will, I think it will be more dramatic here. And by being more dramatic, it will be clearer. And I'll also get into some of the technique. Okay. I need to tell you a little bit about the basics of affine spheres. So, and so these are really, I should say, these are hyperbolic affine spheres. And I have a feeling there's a number of people in the audience, maybe most of them, who know more about this than I do. But, well, you know, I can't see you, so you can read a book. So we're doing affine. For those who don't know it, this subject was very popular in the 1920s, and has retained some popularity throughout time. But it's but maybe the best way to start talking about it is to say, in contrast to Riemannian geometry, in affine geometry, we seek the geometric invariants that we study are ones that are invariant under affine transformations. So in particular, angles maybe don't make sense. Everything that you do has to transform to an associated object under an affine transformation. So all invariants, or feel redundant, are affinely invariant. Just emphasize that. So, and what I'm interested in is two submanifolds S in R3 and their affine invariants. So, you know, I have a hypersurface in R3. It would be nice to have a normal, but angles don't make sense. So I can't talk about orthogonality. But as an example, nevertheless, there is an affine normal. There's a number of ways of constructing this. Probably the most geometric way is, well, you know, the tangent space makes sense. And so do parallel planes to this tangent space. And I'm going to try to construct an affine normal at this point P to a normal to, which is some vector which is transverse to this tangent plane at the point P. Okay, so here's sort of my picture. I have in this case, some convex domain. I have my point P. I have some tangent plane to P. So therefore, I have parallel tangent planes to P. Those parallel tangent planes cut P in some shapes. I'm going to be very sloppy. There's often some volume form, probably always some volume form in the background that I can use to cut it, to normalize things, or when I need it, and volume forms are affine invariants. So with respect to that to the restriction that volume, this area form on this plane, I can find the center of mass, a centroid, and I can do that on every one of these planes that has cut through here. There's another one, and there's another centroid, and I can connect those up. I didn't do this very well, but I will connect up those centroids, and there's my connection, and that defines some, that collection, that curve of centroids has a tangent line, and that tangent line has it's a vector, and then using using the volume form, there's a way of picking out a unique normal psi. So now, where I am in my description of affine geometry is that if I'm given some surface S in R3, I have at every point an outward pointing, in this case, normal, and I'm interested in what's an affine sphere. Well, an affine sphere is an S where what's a sphere? A sphere is a surface where all the normals coincide. Well, meet at a point. Let's say it that way. So you should really sort of imagine that they have these things connected, and they're all coming down to some. It's good if they actually come down to some particular, pole P0. And if you like, now that you have this pole P0, you can sort of project back up to the surface and parameterize the surface through this via directions at an angle from P0. And and so now this, and if you like, if you cut this whole picture with some plane, then you'll get some shadow of the surface S on the plane, and that'll be some domain here over which the surface is a graph as defined by start with P0, go through your domain, I guess I'll call the domain D, and go up to your surface. Okay. So let me think if I've said everything I want to say. This is all, so SL3R invariant using the non-translational part of the affine group on R3. And so this shadow D is some domain in RP2. And so, and we are interested in, and what you find from the theory of affine spheres is that this domain D in RP2 is convex. And so we are parameterizing spheres over convex domains in RP2. Okay. When everything, so I'm looking ahead really to next lecture. So when we have a group action on, say, D or S, then we get and some version of an equivariant map, either an equivariant, either a so-called convex real projective structure on the quotient of D by that group action, or a surface S in space, which on which the group acts and the equivariantly. Okay, but that's really looking ahead, and I will probably say that rapidly again next time.
We have a questions from Rafe. Yeah, you can ask, please.
I just thought thanks. Hey, Mike and everybody. How big can that domain be? Could it be as big as RP2 minus RP1? Or is it always in some sense bounded?
I'm sort of interested in things that don't just have a line as the boundary.
Okay.
Okay. Now, I have to say a little bit more. I'm trying to balance how much I say. Let's see. Okay, I got room. everything in affine geometry involves one more derivative than you would expect in Riemannian geometry. It's kind of just a rule. So the surface, so S has a second fundamental form. Maybe I'll call it H. I said it was convex, so that means the second fundamental form is definite, and so I can regard H as a metric. And when it's regarded as a metric, that induces a conformal structure. Let's see. And we pick up, now I'm skipping steps, skipping a bunch of steps, but I want to sort of just keep the analogy with the previous lecture involved. And the entire setup yields a another conserved quantity, yields a holomorphic, in this case, cubic differential. C of z dz cubed, holomorphic with respect to the complex structure that this second fundamental form defines when you view it as a metric. Okay. From all this, in addition, and so this next remark is not essential now, but here I am, and I will repeat it later. We actually, from all this, we get a map to the symmetric space SL3R mod SO3. And really you want to think of this symmetric space as the space of metrics on R3, right? That's 3x3 matrices up to or change of frame by orthogonality. And what is the metric I have in mind? Well, I'm going to, and so the metric on Euclidean space that I have in mind at a point P is exactly, maybe I'll just write it like this. It's 2 on the tangent space, and then it's on the normal line. Where's my normal? Like on this normal line here. Just take like how long it is relative, or on this normal line. Then if you want to measure a vector, just take like what the ratio of the length of the vector you want to measure to the normal vector. So in some sense, I'll just put it here. I don't have my very good notation, psi in some sense. And that defines a metric on R3, and it defines then also a map to SL3R mod SO3. And so now we have, if we had some sort of group action, now we have a group action on acting on SL3R mod SO3. I'll come back to this in a minute. And this is actually, I won't come back to this in a minute. This is called the Blaschke lift. And if I've done this right, I think I have, then what, and this is actually a minimal map if we start with an affine sphere. So connected to the affine spheres, we end up with minimal maps to symmetric spaces, to this particular symmetric space. Okay, so that starts to connect up to, previously we had a harmonic map to H2, which is a symmetric space. Now I have a minimal map to this higher rank symmetric space, SL3R mod SO3, still non-positively curved, still non-compact type. So you start to see some analogies. Okay. All this is very abstract. You've never seen it before. It's time, I think, for some examples. So there's two examples that come to mind. The first is I can take S to be just one sheet of a hyperboloid of two sheets. So, this Minkowski model of hyperbolic space. I have a hyperboloid. This is going to be a graph over a circle. It's just whatever. So if I start down at some polar point, let's make it some polar point here and go straight up, then the action is just to get from here to here. You just do something in SO21 and you can cover the whole sphere. So this is, you cover the entire, sheet of the hyperboloid. So this is picking out an SO21 inside this SL3R. And so when I think about what the image, just say the image under this Blaschke lift to the symmetric space SO3 that I called X is just some copy of hyperbolic space. Because SO21 has to carry, its action has to carry over to the symmetric space, and what's it going to preserve? Will preserve something hyperbolic. Okay, that's some example. Oh, I should tell you. And so what is the cubic differential in this case? It's 0. So do I have anything else I want to say about that? No, I'm not going to say much. Now, that's example 1. That's probably a guess, interesting guess. Example 2 is actually our more basic example. It's a due, I guess it's due to Titeka. I'm now forgetting my history. And this is Titeka surface, and I'll call it T. And this is going to be a very basic surface for us. So Titeka was a mathematician early part of the 20th century. I think I have this right. I think he was an ICM speaker 6 times. Just a factoid. So this is the surface. So S here, there's a number of ways of defining it, but S, or to T, is the surface defined in R3 with the coordinates x, y, z by x, y, z equals 1. So you can sort of see it, right? You draw it. I don't know if I can draw it well, but it climbs up the axes and clings to the edges of it clings to the first quadrant, and I think you can imagine it better than I can draw it. It's a graph over, I don't want to use that color. It's a graph over a triangle, say from this origin. And so that's the RP2 structure. And so you see the huge difference between the Titeka surface and the hyperboloid is that this is perfectly round, and this and the defining domain, or the real projective domain for the Titeka is a triangle. There's no roundness to it. And let's see, what should I say? And in this case, the cubic differential is 1 dz cubed. So, we mentioned last time that if you're doing if you end up with something holomorphic, then you have two types of behavior. You have the behavior near the zeros, and you have the behavior away from the zeros. So in some sense, when we're studying a arbitrary cubic differential, we now know what to look for, right? Because near the zeros, we should be looking for something that's kind of hyperbolic-ish, or something like this sort of hyperboloid, something like hyperbolic space. And if we're looking away from the zeros, we should be looking for something that's kind of like Toteka, because that's with a cubic differential there would be 1 dz cubed. So why are we looking at this? Let's see, do I want to say anything else? Oh, I should say also, you notice the invariance here that, if I have, say, given a point x naught, y naught, z naught, maybe on Toteka, then given any other point x, y, z on Toteka, I can divide. I can have an action just by dividing by the original coordinates, and I'll stay on Toteka. So in other words, we have invariance by an R2 action. Just you take your favorite x naught and y naught, you can compute, that z naught is 1 over x naught, y naught, and that will, and so points in R2 will move Toteka to itself. So this has a flatness to it, and so the under the Blaschke lift, the image of T is a flat in this symmetric space X, which I defined up here. So again, we have very differing behaviors. The images here will be a flat, something totally geodesic and isometric to Euclidean space, and the image up here is a copy of hyperbolic space. Okay, why are we looking at all this?
Can we have a question?
Yeah.
I wanted to ask, image by the minimal map? Is that what you're saying?
Yes. I said that there's this underlying conformal structure. And I said there's this Blaschke metric defined. I'm sorry, we back up. I said that there's a Blaschke metric defined by the second fundamental form, and that defines a conformal structure. So I have this Blaschke metric is giving me some conformal structure Z, and in that I can maybe write the Blaschke metric as e to the u dz squared. I've also told you that somewhere around through the genius of the folks in the 19 teens and 1920s, they discovered this Pick differential. I'm not sure it's due to Pick. I've forgotten. I'm sorry about that. The dz cubed. And these two are invariants. Well, they're more than invariants, because what I can imagine is that if I have, this domain, and I have, some D, and I have a point here, and then I represent the surface by the affine normals by some function f, then I could write as a frame f as the affine normal and a complex frame fz bar. These last two will parameterize the tangent space at a point, and this gives some frame which I'll have trouble drawing, maybe here and there on for R3, that when I look at how the tangent lines get developed will define the surface S. So if I have this frame field, then integrating the planes that give the last two elements possibly defines a surface as long as it's integrable. So now I want to so what is the integrability equations for this? To the integrability equations are, well, I already told you that the differential should be holomorphic, and the major equation, or the equation we'll end up studying, is this one. In terms of this conformal structure, the Gaussian u is 2e to the u minus 4e to the minus 2u c squared, and then some sort of curvature term like we had. So now maybe you start to see why I bring this all up. This equation looks an awful lot like the harmonic map equation we studied in the SL2R context. And, we still have a holomorphic form, and, it still has, the right signs. And in particular, this was highlighted last time. If I call this right-hand side, I don't want to call it F anymore. That was stupid. Oops. Well, I used to call it F. So the right-hand side, which depends both on a point Z and on U, it is monotone in U, just as the other one was. So this also has a maximum principle and also admits sub and super solutions. So in fact, using last time's discussion, we already know a lot of existence theory and estimates on these affine spheres just by looking at this equation and realizing it's the same equation. So, oops, out of space. So I will call, so this equation is due to C.P. Ouyang. Last time I called the equation B for Bachner. Now I'll call this one W for Ouyang. That's the Ouyang equation. And just to, and I guess I still have to tell you one more bit of analogy, is that last time you remember, I only needed to know U and C. I only needed to know this holomorphic energy, which satisfies some equation like this, and a holomorphic, holomorphic energy and this holomorphic form, and that determined the entire pullback metrics. That's all I needed to know. Here, so here the relevant thing, and I'm going to do something which I think is probably a waste of time, but when I look at this pullback of the frame, so this is, some element in GL3 C, I guess, the way I've set this up. I pull this back and I get some matrices DZ and some matrices DZ bar, and I'll write down the first one. The second one has the same qualitative form, 1/2 e to the u 1 uz 0 c e to the minus u 0. All right, and my point in writing this out, later I'll refer to this. You see that, first of all, this pullback frame only depends on C and U. So once I know C and once I know U from this equation, or given C, if I can find a U which satisfies this equation, I can write down this frame field. These are the integrability equations. I can get a surface. And the frame field, and it's explicit. That's something I'll use, is that I know what this thing looks like. And I know there's another term over here where these terms with the e to the u's are in different positions. And the positions they're in are geometrically interesting, and I'll come back to that. Okay. Wow. I don't have anywhere near the time I thought. Oh, one more analogy. Notice, okay, I'm just gonna put one more thing in here. That if in the Titeka case, where C is 1, then U is log 2 to the 1/3. Okay, so that's a solution. And this is a constant, of course. Okay. With all that, here's what I want to prove. To show. You recall H2 from last time, we had a correspondence between polynomials P of z dz squared. I did the z to the k dz squared. I just did the single zero, but everything I did with sub and super solutions will work if you have a finite number of zeros and polygons. So now in these RP2 structures, I want to have a correspondence again between polynomials c of z dz cubed and some sort of and polygons in RP2. Okay. So these are going to look like, so here I am in RP2, and I'm going to have some funny polygon like this, and then I won't draw it, but over this polygon, we're going to have some surface. Okay, so in the previous setting, the boundaries being geodesics were kind of obvious. So the question is here, what should I think of as geodesic boundaries? And well, the basic objects are these Titeka surfaces. So the setting to keep in mind is, recall that when we have a constant cubic differential, this is corresponding to a triangle. Remember that Titeka was a graph over a triangle. So what is the boundaries of this polygon in RP2? Let me redraw the polygon. So if I have some polygon like this, then a boundary, let's use different colors, is going to be like a triangle. That'll be like what we're expecting as we go near the boundary to see a geodesic, but the analog of geodesics are triangles. So we see a triangle there. And we might think that the adjoining geodesic, the adjoining triangle, is the next one like this, but we have to remember that we're in RP2. So this pink triangle is in some sense, centered at that point. And so next to that point is an edge. And so the next triangle, so if this is triangle 1, then triangle 2 is going to be centered on the edge, and it's going to look something like this, and in RP2 it'll come back like this. So this is really triangle number 2. So this pentagon has 10 boundary objects, and those boundary objects are triangles. And as we move from one boundary object to the next, we do some sort of flipping. And this flipping is going to be very much like the flipping that we did on the boundary geodesics. It's really, I'm going to run out of time. This is really flipping between flags. So, really at every point I have a pair. You think of having a pair of vectors. So I would have 10 of these, and I'll go from this pair of vectors to this pair of vectors. That's the next pair. And so that corresponds to triangle 1 centered at this pair of vectors, to triangle 2, which the two vectors share an edge rather than a vertex. Okay. Now, so I want to try to focus on this issue of Stokes directions and flipping. So, oh boy, how am I going to? Oh, I can do this maybe. So let's just think about C. Maybe I'll say C is dz cubed. The picture here is more complicated than it was in the quadratic differential case. So here I'll have some singular lines that maybe look like this, but they're more singular vector fields. And in this case, I'll have 8 singular vector fields with arrows alternating whether they come into or out of the origin. And you can sort of follow one of these vector fields along. You can sort of see, well, near this one, I have this sort of vector, and it kind of just curls along here. So what that means is that this region here with 3 of them is like a half plane. So really I have some half plane here with, which maybe I should draw this way. I have blue going that way, and I have green coming into it like that. And then this is, that's the half plane is, if I didn't, maybe got myself confused, is up here. And then I have a couple other singular lines coming out of this, a green one and a blue one. And the green should have gone in and the blue goes out. So, sorry. Okay, I have some sector like that. I know this is a bit fast, but I'm going to try to get to a point. Here's the basic question. I'll be able to convince you soon enough that in some appropriate sector, something like this, in some appropriate sector, I'm the same way that we were rapidly asymptotic to a geodesic in the lecture last time, that when we went out far enough away from a zero, we had a solution that was basically constant, and the map was the map you would expect for a constant holomorphic differential. So in some sector, you might start to believe that that the image is some triangle. And then, in the next sector, you might start to believe that it's some other triangle, which I'll just draw schematically like this. And so you might start to think that, okay, well, now I see a polygon, right? I see like one edge and then another edge. But the problem is the transition? How do you know that the image of this polygon, maybe it's kind of straight here and maybe it's kind of straight there, but you're taking limits. How do you know it doesn't like curve as you go? So sure, it's kind of like straight as you go out, but how do you make the transition from one side to the next and keep it straight? This is a really vexing problem for Emily Dumas and me. And this requires somewhat finer analysis. So to do that, we require a finer analysis of W than we did earlier of B. And here's the point, is that, so we're looking at this equation, Laplacian U equals 2e to the u minus 4e to the minus 2uc squared. There's no curvature because I'm on the plane. And, we've already said that if C is 1, then U is log 2 to the third. So if C is like 1, U is this plus an error. Okay, so what's the error? And we can plug in, we can look at what the equation for the error is, plugging in U and plugging in C. And what we find is this leads to saying that the error looks like Laplacian E equals 12E plus some higher order terms. Okay, so that's the deviation. So when you're doing one of these asymptotics and you want to know what's, how close are you? Well, this is the equation. You end up with an equation for the error. Okay, so what's the geometry here? And of course, so this is when it's rotationally invariant. So the error is then some Bessel function 2√3r. And Bessel function, so this is saying that this decays like e to the minus 2√3r over square root of r. So that's pretty fast decay. And so that's feeling pretty good. So I'll just say that's, that this is kind of the error equation. And this looks like really fast decay, right? Well, there's a problem. So, fast decay. Well, there's a problem in that let me do a quick computation for you and show the problem. And oh gosh, I'm going to run over again. But I started 2 minutes late. I don't know.
Yeah. You can take some more time, maybe 5 minutes.
How much time can I take, really? I don't want
to. 5 minutes. 5 to 10 minutes.
Okay. I'll try to wrap this up because I'm almost at the point. I very much regret what I did earlier. Okay, so we're in frames. So the frame. So let's think about that. The problem is that this error has to be understood in terms of the frames. So my frame field solves some equation like df is af. The Titeka solves some equation like dt equals bt. So if I want to compare my frame to Titeka, I want to look at T inverse f. So I take d of this, and we do the chain rule, and I get a minus T inverse dt, T inverse f, and then a T inverse df. But this is AF. This, oops, didn't mean to do that. DT is a BT. So I sold the T inverse the F, the minus T inverse this. This cancels. And when we just quickly get to the answer, so I'll have a T inverse an A minus B, T, and then a T inverse F. That's just algebra, trust me. So I can look at the difference between those connection forms, A minus B, and that's going to involve this error. So this part here, so here I'm going to have this e to the minus 2 root 3r over root r, but it's being conjugated by this t, and these can be growing. So in that, don't mess up the colors, but in this upper half plane, along some directions, in most directions, t in like this direction, the t is much, much less than e to the root 3r. So I will get this sort of rapid convergence of the frame to the theta. Similar in here, that t is much, much less than e to the root 3r. Along some lines, t is actually like root 3r. So it's actually balancing between what is decaying from our equation and what is growing in the other direction. So, so that feels bad. But here is the point. Why I bring all this up. What is the geometry here? So this is really like a Gaussian viewed from infinity. Normally we write Gaussians, the kernel of the heat equation around the origin, but now look at it infinity, set things up properly, and you see the r and the root r that should look sort of suggestive anyway. And the point is this, that as I transition from here to here, and I transition further and further out, this Gaussian starts to take over against these t's, and we get something singular. And that, if you remember this equation for the frame F, which had some matrix, dz and some other matrix dz bar, this becomes along these lines something that looks like ones down the diagonal, zeros everywhere, and in some spot in like a number a. And what this is, so this unipotent is acting on the triangles. So this unipotent is taking a triangle like this to another triangle like that. And so because we see in the asymptotics this unipotent, that is saying we have exact asymptotic, we have that the boundary of this shape is exactly described by triangles connected by a unipotent. And that's what gives the sharpness. And I just think it's really cool that you study this Ouyang equation, you look for the error. The error is a Bessel, but it has geometry. And the geometry of the Bessel is that it's a Gaussian, and that Gaussian is telling you that you have this Stokes change from one triangle to the next. And so I ran late. I'm very sorry. I will stop there. I think that's actually an okay place to stop.
Are there any questions? Yeah.
So you mentioned one matrix where you had the second fundamental form in psi. So is that a metric that you actually get, Blasch's metric?
So the way I find geometry, I'm not sure I understood the question. Let me
There was a matrix where you wrote a second fundamental form on the psi.
There's a couple of things. So let me try to respond. You tell me if I responded properly. So in affine geometry, just everything seems to go up one derivative. So you look at on a surface the second fundamental form to the surface. That's if it's a convex surface, that form has is definite. So I have a symmetric, definite quadratic form. Let's call it a metric. Okay, what's a metric? It's a symmetric quadratic form attached to your manifold. So I'm just going to call that a metric. That's going to be the Blaschke metric. Now, yeah, and this is the problem with a slide talk or a even worse. Oops, wrong way. This metric. Is this what you're talking about? This matrix. This. I showed two matrices. I showed this one, and I showed this one. The first one was the sort of Blaschke lift to get me to the symmetric space. You just put. I wanted a metric on R3, and so I made a metric on R2, and then a metric on R1, and I declared them to be orthogonal, because this normal vector is transverse to the tangent plane. So I'm just going to say the tangent plane is orthogonal to the direction in space given by the normal line, this affine normal. I mean, the way we look at it, it probably isn't, from our notion of Euclidean 3 space rather than R3, but we'll just declare them to be orthogonal, and we'll put some scaling on the transverse line and make that a metric on R3. Once I have a metric on R3, then I have a point in SL3R mod SO3. That was one matrix, and so I'm wondering though if I also wrote down.
Yes, I actually wanted the previous one. So is that a metric on the quotient SL? Is it an R3 or?
This is a metric on okay. I have colors, I guess. I have RP2. I have my surface. I have a point P, and now the tangent space at P to R3 is an R3. Okay, I'm not doing the tangent at the tangent to the surface. I'm doing the tangent to R3 is an R3, and so and I'm decomposing that R3 as a tangent plane plus an affine normal line, and I'm going to put a metric on that R3 thought of as a tangent space to R3 at this point. So therefore, I have a map from the point P to
yes, got it. Yeah.
A 3x3 matrix, which is block. I have the 2 up and the 2x2 up here, and then a 1 down.
Just one more question. So you also mentioned something about when you are considering this map from D to H2 cross H2 to R, the distance function. So you mentioned something about using the D square being subharmonic, but you also mentioned something about the lower bound that in terms of D square you can't get. But in non-positive curvature, you do have something like lower bound with 1, but you want, I wanted to understand the argument you wanted to make there, comparing with something lower where you also have something like C D square. So in general, you do have, when non-positive, you have a lower bound, but
Okay. You're not going to get, in general, when you look at the Hessian, you're going to, you won't get this sort of bound in general. I mean, that's why I crossed it off, because, if you're in H2, what do I want to say? So if I just map to a geodesic, I could like slide along the geodesic. So if you look at the Hessian, the distance between here and here, there's some direction to move both of them where the distance does not change, right? If I just slide each of them in the direction of the geodesic between them, then that is the Hessian with those two vectors is 0. So you have to think a little bit about the map U and V, and so each of them has a frame, and you have to think a little bit about how big the frame is, and make sure that you have some vector that's like orthogonal to the distance between them and how big that will be. And when you do that sort of analysis, you can get something a little better than 0 on the right-hand side. But you have to do something, it has to do with knowing at least one of the maps.
Okay, thank you, sir. Thank you.
Are there any questions?
Okay, well, thanks for staying up late with me.
Mike, sorry. I think it's more conceptual than technical. You started out yesterday with the the map into hyperbolic plane, and you explained then you have this boundary. You have the image of the map is ideal.
Yeah.
Bounded by ideal
by geodesics
and so on. So okay, fine. Now you are. I think the transition I didn't get is the following. Here you now study a harmonic map, actually a conformal harmonic map.
Yes.
Into this symmetric space of Euclidean metrics on R3, right? The X you call it.
Yeah.
So why wouldn't and then you said now replace the geodesics by the essentially by these real projective structures, right? But in the domain of RP2, I would have imagined that you now have a polygon in this space X, whose boundaries are kind of geodesics and so forth. I mean, but that's not what you're doing clearly. You see what I mean? Or do you replace the geodesics by flats? Is that what you do? What I should think of? Instead of geodesics before, now you're thinking of flats in this space.
Yeah, I mean, the Tatekas are really flat, so sort of like these asymptotic flats. And if you think, so the Tatekas are the basic object. And so they have this, so geodesics, we know what they look like, right? They're like these straight curves. The Tatekas are the same sort of basic objects. The Pick differential is constant. The same way harmonic maps through geodesic have a Hopf differential, which is constant. So and so they are forming, if you think about like the asymptotic frame field in each setting, on the H2 setting, the asymptotic frame field becomes tangent to a geodesic. Here, the asymptotic frame field becomes the frame field for a Tateka as you go further and further out. The osculating, maybe it's a better way of saying it, the map which osculates at a point to the image would define a geodesic in the first setting and define a Tateka in the second. So in the first case, yes, that's what I'm trying to get across, I guess, is that you have in the plane, so here I am in the plane, oops. And I have these like sectors. And, in the first setting, in each setting, I have, in each sector a very basic object that within the whole sector the map is converging to. So in the first setting, it's a geodesic, and in the second setting, in this RP2 case, it's a Topology. And in both settings, as you so you have different asymptotics. I should really do this in color, I guess. So over here in the green sector, I have another geodesic, and in this analogous green sector, so I'm drawing the same picture twice, but it's a lie because they're not really the same picture. I have some other Topology. And the point is that in both settings, you have this transition between the two, which is a flip, some sort of unipotent. It's not so apparent in the simple setting, right? You move from this geodesic to that geodesic, from this flat to that flat as an asymptotics. It's for me anyway. I didn't appreciate that until we're in the more complicated setting. Maybe that's just a personal statement. Is that collection of ramblings at all?
No, that explains it. Yes.
I'm not hearing anything.
Okay.
Are we done?
Okay, so you have said that okay, so you have mentioned that image of the trace surface in the symmetric space is a flat. So is that flat maximal?
Can you say it again, please?
Okay, so you have mentioned some time ago that that image of that surface in the symmetric space SL3R quotient SL3R is a flat. So is that flat maximal?
Yes, it's a rank 2 symmetric space, so that's a two-dimensional flat. There's lots of flats, of course. And really what's going on in some sense is when you move from one to the other, I didn't get this far into it, but you notice that, so let me try, I guess I might, I had a polygon, and I think the polygon was black. And then I have this polygon, and then this was one triangle, and then I had the next triangle like this. And you see that these two triangles share a lot, right? In particular, they're sharing, this edge. What's happening is, and I guess I should say more, if I think about these sort of flags on it, they share this flag, and this flag. So they're really sharing, I hope I have this right, and Charles and Parker will just correct me quietly and politely later at lunch. But they're really sharing 3 vial chambers of an apartment, but the other vial chambers are moving, so between blue and green. So they'll have different vial chambers. And so you'll have these 2 flats which are sort of asymptotic because they have 3 vial chambers in common, but the back ends will flip in very much the same way that in the geodesic case, you have this geodesic and this geodesic, which are forward asymptotic, so they sort of share half a vial chamber, which in this case is just 2 of them. And then, but the backwards one is different. So they, they share the common front points. They share the common front points, but what's going on when you flip is you flip the back file chambers to the other sides of the flat. I know this was very fast, so I apologize for that. I hope there's some at least impressionistic.
So I think we don't have any other questions. So let's thank. Yeah, thank you very much.
You're welcome. Thank you.